Hey guys, we're going to start Vodcast 10.1. We're going to talk about solutions. This is going to be kind of a short Vodcast because we're just going to sort of review some ideas from when we talked about this in the beginning of the year. If you're looking for more of this, you want to jump back to Unit 2 where we talked about some of this stuff. I don't know about more detail, but again, and that might give you another hint about what we're going to do. So first off, what is a solution? A solution basically is a mixture in which everything is completely dissolved. Okay, that when you look at it, everything looks pretty much the same throughout. So like, of course, our ubiquitous example that we've used tons of times this year has been that of sweet tea. So you have sugar, and then you've got a bunch of other chemicals, the stuff that's involved in the tea, and they're all completely dissolved in the tea, at least if you've made it right. You could leave that tea in the fridge for a couple of weeks, and it's probably going to be the same stuff throughout that time. Nothing's going to fall to the bottom. It's not going to separate out. It's all one essential thing. Now, just to review a little bit, if you think back, we talked about colloids. And specifically, we talked about colloids like blood and milk, stuff like that, that they're a little bit in between a solution and a heterogeneous mixture that we'll talk about here in a second. They look like they're sort of one thing, but they're not totally. And the reason that I have this weird, you're like, what's up with the nature picture, Arnold? The reason I got this picture up here is because one of the examples that we talked about really briefly before is that of fog. Fog is a great example of a colloid. You have droplets of water that are suspended in the air. A cloud, by the way, also same sort of deal. You got droplets of water that are suspended in the air, and it looks like it's all one sort of uniform thing. And sometimes, in fact, you can't see it at all. But what happens is that as the light goes through it, it starts to get all foggy. Okay, it starts to show that it's there. It looks like the air is all dusty and stuff. That is a colloidal mixture. Okay, so there's a lot of water vapor in the air. The air or the light through here is going to show that up a little bit better. Remember, we talked about it at the very beginning. Okay, hold on. Okay, so we talked about that at the beginning. If you remember, that was something called the Tyndall effect. Okay, Tyndall effect, remember, is where you shine a light through it and it gets this nice sort of cloudiness. Of course, is what makes it easy for us to tell the difference between a colloid and a solution then. So then the next thing that we have are heterogeneous mixtures, okay? Remember, heterogeneous means that two things are different from each other. And so this is a pretty good example of this. This looks like a glass of milk, but what this actually is a bunch of flour put into some water, stirred up. And of course, after a little period of time, what you start to notice is that it starts to separate out. So if you look right here at the top, okay, in this area right here, you're starting to see a layer where the water's starting to clear and the flour is going to go down. And if we let this sit for maybe an hour or two, you'd probably see it down here. And maybe over a couple of days or something, the flour would be all down here at the bottom. The water at the top would be pretty clear. That is a suspension where the particles are so big that if you're not continuously stirring it, they start to fall down out of the solution. Okay, so back to the idea of solutions. Solutions are homogeneous. Okay, that is sort of the defining thing. A homogeneous mixture of any kind can be called a solution. So like when we talked about alloys before, where we got two different kinds of metal that are mixed together, that is a solution. It's a homogeneous mixture. The way that we're going to talk about it most of the time in chemistry, of course, is that we have a liquid, typically water, we'll talk about that in a second, that we're adding some chemical to and we're stirring it all up, okay? That is our normal solution for us, and we'll see that that has a special name too. So the first thing we need to know is that there are specific definitions for these things. And the bad news is they kind of all sound the same. So solution, solute, solvent, all those words sound pretty similar, but let's go through them real quick just to make sure that you know how to define them. The solute, okay, is the stuff that you are putting in to dissolve. So like in this case, I'm dumping some salt into a glass of water here. The salt is the solute. That is the stuff that is going to be dissolved. The solvent is the stuff that's doing the dissolving, in this case, the water. Okay, so in this particular example, we got solute of salt, solvent of water. Okay, just got to keep those two terms kind of separate from each other. Now, A couple other quick things here. We said that we're going to use water a lot. Water is used so much that it has a special name. It gets called the universal solvent. Okay, why is it called the universal solvent? Because it dissolves a lot of different things. We're going to talk here in a second about what specifically types of things it does dissolve, but it dissolves a lot. That's why we use water to clean a lot of things. That's why we use water as our base for a lot of things. Really, to be honest, life is only possible because of the solvent capabilities of water. Your blood in your body has water as a solvent with a whole lot of solutes dissolved into it. So water is pretty important. So therefore, we're going to call it the universal solvent. Now, since it's so important, we use it so much, solutions where water is the solvent have a special name. And we already know this name. We've talked about this before. If you recall, we did things like if we had that cup of salt in there before, we would say that that was NaCl, but that it was aqueous. Okay, so aqueous basically just means that something is dissolved in water. It's kind of one of the fourth phases of matter for us in chemistry. But of course, I guess fifth phase if you include plasma. But really, we use solid, liquid, gas, and then aqueous solutions a lot in chemistry. Okay, so mostly all definitional stuff, right? Okay, that's that first video. Make it a little easier on you. The next definition that we want to talk about is something called dissociation. I know this is kind of a busy slide compared to what we normally do in class, but here's what I want us to look at. We're going to talk about the dissolving process of sodium chloride. So I've kind of got this graphic here. That might make sense to you, but I have a feeling that it probably doesn't. But basically, remember that this is what I want you to look at. If you see down here, this is a salt crystal. Okay, chlorines are the greens. Right in here, the grays, those are the sodiums. And what's going to happen in the dissolution process, let me shrink this down a little bit. What's going to happen in the dissolution process is this. Water molecules, if you remember, they are polar. So they have a positive end where the hydrogens are, and they have a negative end where the oxygen ends are. Okay? And so if we're attacking an ionic compound like salt, remember that the sodiums all have a positive charge. Okay, if you wonder why the sodiums are like this, remember sodiums are going to be smaller than chlorines. Okay, and then the chlorines, of course, all have negative charges on them. So what happens is that the water molecules are going to come in here, and the negative ends of the water, where the oxygens are basically going to pull the sodium away, and then all of that stuff together, okay, is essentially going to just pull it away from the molecule. And then that's going to happen again and again. Another water molecules are going to come up here. Okay, let me get rid of all these positives here, guys. Sorry. Another water molecule comes up, and that water molecule steals that end of the molecule. Okay, so it takes away then that sodium. All right. And then the water molecules, if they were turned the other way, so some of them are oriented the other way with the negative ends, the hydrogen ends facing the crystal. And when that happens, those negative ends, they grab a hold of the chlorine, okay, and they're going to pull it away. And so that process goes on and on until it's all dissolved, and that process is called dissociation. We take a compound and we break it apart. Okay, we dissolve it basically. Okay, so one more quick term that I want to talk about here. If you look at something like, I'm sure you've done this before, maybe you just got some salad dressing at the restaurant and you noticed maybe that it was separated. You had a layer on the top of a lower density, like oil, and then a layer on the bottom of a higher density, like water. So if you think back to the density columns that we made at the very beginning of the year, we had multiple layers of this, right? And the reason that those density columns work is that not everything is going to dissolve in water, okay? Only certain things dissolve in water. And here's the way it basically works. The general rule is that like dissolves like. You'll hear that term a lot used in science. So what does that basically mean? Okay, here's what it means. Polar solvents, okay, so water is polar. We've talked about that a ton of time. Polar solvents, okay, are going to dissolve polar, or you could say ionic, solutes. Okay, and then what would be the corollary of that is that nonpolar dissolves nonpolar. And so why doesn't this work out here? Okay, like why do we have like water and oil and they're not mixing together here? Well, pretty simple. Oil is nonpolar, okay, water is polar, and so therefore they're not going to mix together. And in fact, we actually even have a special term for the fact that they don't mix together, and that special term is immiscible. That may be on your notes or not. If it's not, you can go ahead and copy this term down. Immiscible means two liquids that do not mix, and that is the opposite of miscible, which means that they would mix. So like if you took if you took something like dish detergent, which is in a liquid form, and you put it into water, mixed it up, that dish detergent is going to dissolve. They both have polar ends on them, and so it's going to dissolve it. But oil, which is non-polar, is not going to dissolve in water. And that's why, like, when you try to wash your dishes at home, with just water alone is not going to get all the grease off the dishes. You have to add something to it, being the soap, to help dissolve that, because soap has a polar end and a non-polar end. We're not going to get too much into that, but that non-polar end helps it to dissolve the grease that water can't on its own. If you ever had like a grease stain on your shirt or something, you try to wash it out with water, that's not going to work. You need some soap to be able to get that out. And it all goes back to this idea that like dissolves like. Polar things dissolve polar things, and non-polar things dissolve non-polar things. All right? Thanks, guys. I know that was a lot of definitions. We're going to get into the math here in a little bit in the next section.